Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my channel I deal with different aspects of mathematics, physics, chemistry and biology. And today we are going to look at a concept of heat capacity. Now the concept of heat capacity basically deals with the temperature or the heat energy that is required to raise the temperature of a given quantity of a substance by 1 degrees Celsius or 1 Kelvin as we are going to see later. So we can be able to describe temperature in terms of kelvins or rather degrees Celsius, but basically the concept of heat is going to be involving that particular aspect of a change. And this is going to involve, the heat capacity is going to involve systems particularly which are going to be undergoing a change whereby there is no change in what we refer to as a phase. And in this case, for phase, I refer to solid, liquid, and gases and different forms of matter in this specific case. Now, the increase in temperature, the change in temperature is going to be denoted as dT. And in some cases, of course, as I've said, we are going to use the notation for delta given as such. So if we try to consider this aspect of temperature, I'd say from a discussion on our first video that basically the amount of temperature is going to be proportional to the amount of heat flow, especially for a system of this particular transfer of heat. If I say if this is a gaseous or liquid state, then therefore if this increments in temperature, then therefore it's going to be proportional to the heat flow. And we can be able to illustrate this in terms of an equation which is going to give us a relationship as change in temperature and also the change in heat Q. So these two aspects, of course, are going to have a relationship whereby we are going to see that the change in temperature is going to be directly proportional to the change of heat energy, and that relationship is going to be given as such. So if we try to give this in terms of an equation, we're going to have this one represented as this specific constant given as such. So this relationship that exists between the two can form a ratio where we're going to see that dt over dq is going to be given as C. So this C is going to be referred to as the heat capacity. So therefore, different forms of substances have different heat capacities. And of course, they are going to vary depending on the nature of substances, especially through different phases. Of course, whenever we're trying to consider the aspect of temperature and pressure, say. So according to the first law of thermodynamics, we are given a relationship between the energy, the work done, and the heat that was involved, whereby we say that we can be able to give a description of this relationship from the first law of thermodynamics, whereby the change in heat is given as the sum of the change in energy, which was delta E, and then the change in volume under constant pressure given as B dV as such. So therefore, we can be able to describe this one having said that if the heat capacity is given in terms of dq over dt, we can be able to give a relationship that is going to, of course, be derived from our first, skip this one as our first equation. So therefore, we can be able to describe our first equation from the first law of thermodynamics in form of a heat capacity, whereby we are going to divide this equation by dt. So therefore, we're going to have a different version of this equation, of equation 1 divided by that one, given as dE over dt plus b dV over dt given as such. So this is going to form our equation 2. And therefore, from that specific description, therefore, we can be able to give that relationship. So at constant volume, the heat capacity then therefore is going to be described using or rather, we can just have this specific heat capacity at constant volume being given as CV, and CV in this case is going to be described using the ratio between dE all over dt and a constant volume given as such. So this is going to form our third equation. So from this first law, we can be able to describe the heat capacity in terms of a constant volume. And at constant pressure, and therefore we can have a specific description for this heat capacity using the constant pressure given as such. So heat capacity under constant pressure, which is going to be described as dq over dt, and we can be able to give this one under constant pressure. So I'm going to use those specific parentheses describing that. So I'm going to have dq over dt, that one under constant pressure given as such. So this first one is under constant volume given as such, and this is going to form our equation 4. So given as that one. So therefore from that one we can be able to describe dq using the aspect of that extensive property of matter that I had mentioned in our first video, whereby we see that this extensive property of matter, which was described as E plus BD PV, of course is going to be referred to as H, which was of course what I referred to as enthalpy. So therefore, having looked at this relationship of constant temperature, pressure and volume, I can be able to describe heat capacity in terms of that particular description, whereby I'm going to have dq is equivalent to dH, which is change in enthalpy, and then I'm going to have that one minus V dP given as such. So therefore, the CV that I've given in this case, which is a heat capacity under constant volume, is going to describe the rate of change of internal energy with the temperature, which is going to be at constant volume as I've given, and the CP is going to represent what I've referred to as the rate of change of enthalpy with temperature at constant also pressure. So what are the implications of these specific equations? So the ratio between these two heat capacities at constant temperature and pressure of this particular system are going to give us a particular ratio, which we are going to consider, of course, in the gas laws, and it's going to be applicable for monoatomic gases and the diatomic gases and perhaps triatomic gases, but we're going to consider, of course, an aspect for monoatomic gases and diatomic gases respectively. So in this case, I'm going to give an example of gases, e.g. helium. So in this case, I can be able to give this, the CP, or rather the CP. So this is a CP over CV value, which is going to be represented as R. So we can be able to consider the case for gases, which we have said I'm going to consider for the monoatomic and diatomic gases. And if you try to look at the monoatomic gases, they are going to have a constant value for R, which is of course 1.67. And for diatomic gases like CO, these are going to have an R value of 1.4. And this, of course, is going to be more elaborate. So in trying to describe the concept of heat capacity, we're going to see that there are some equations and ratios which are going to be developed in this particular case. And they're going to assist us evaluate especially that aspect of matter which does not involve a change of phase, but involve the change in volume, temperature, and perhaps the concept of pressure, by trying to maintain one variable and then perhaps trying to vary the others, and then trying to see how they can be able to be described. So the various equations that I've given on the board for 1, 2, 3, and 4, of course, are going to give us one aspect of describing various ratios for heat capacity, especially for the last one that I've mentioned for monoatomic gases, example of helium, and diatomic for carbon oxide given as such. So catch us in our next video as we're going to look at the difference between this CP and CV for an ideal gas, whereby I mentioned in our video that this, of course, is going to be a series of relationship between the fundamental laws that we're going to encounter in different phases of matter. And this basically, as we have mentioned, are going to affect the concept of gases. So this one, so we're going to borrow them in our next discussion, especially concerning the concept of the ideal gas, which we are going to discuss later. So this is it for now, guys. Bye. God bless you. Catch us in our next video.